I think we left off last time at approximately somewhere around page 26 or 27. Okay, there we go. Got that done. All right. And so let's actually pick up on page 27. All right. And so last time we did 1D motion, I think in the X direction. I wanted to say a couple of quick things. Whoops, come on. There we go. About 1D motion in the Y direction near the planet Earth, which is pretty common. So just the simplest version, right? If I just throw a marker up in the air, right? Maybe it's going a little bit at an angle, but if we ignore the angle slightly, it's going pretty much straight up and down. You can think of that as 1D motion, right? All right. So this is a very special type of 1D motion. It's called free fall. Gotcha. Whoops. Get those people in here. Sorry, I didn't hit the button faster. Let me make Jules co-host too. Okay, so let me do that really quick. Sorry about that. I just got you all in there. We haven't gone anywhere yet. All right. Okay, so free fall. Now, free fall, you may not think of it, but when I throw a marker straight up or even at an angle, that's free fall. Free fall is a term that means gravity is the only force acting on object. So to be clear here, when I throw this marker up in the air, you might be saying, well, wait a minute, isn't there some air resistance? Yeah. So there's a caveat for air resistance is definitely a force, and it definitely matters, right? If we didn't have air resistance, our cars would get a lot better gas mileage. Okay, so air resistance is often considered negligible. And to be clear, for test questions, we oftentimes assume air resistance is negligible, even when it's not even close to being negligible. Otherwise, the problem gets so hard you have to code it. And it's actually really easy to code problems with air resistance. It's just difficult to solve on paper and pencil exactly, or analytically, as they say. So this word relatively, I'm not even going to elucidate what I mean by that, but I could say this at least, right? If you're moving less than 5-10 miles an hour, air resistance is pretty negligible. 20-30 miles an hour, if you put your hand outside a car that's moving at 20 or 30 miles an hour, you might notice it. So yeah, somewhere between 10 and 30 miles per hour, air resistance starts to become really significant. All right. So yeah, you could argue maybe relatively would mean less than 20 miles an hour or something like that. Whatever. Okay. So that said, let's take a look briefly at problem 2.8. Right? 2.8 at the top of page 27. Take a second, discuss with your neighbor, just get warmed up, talk about it. Which of those do you think is free fall or not? And talk, yeah, if you want.
Just a question.
Yep.
In higher altitudes, is air resistance less significant than lower altitudes? So like in valleys, let's say a top of a mountain or in a valley.
If you're in outer space, there's negligible air resistance, right? So clearly, as you go higher and higher to less atmosphere, atmospheric resistance, right, would depend on the amount of atmosphere there. So absolutely, as you go up in height, yeah, even crazier, air resistance can speed you up at high altitudes at the edge of space. I don't want to talk about that. I'll tell you later. All right. A little bit of air resistance can actually cause you to go to a lower orbit and convert gravitational potential energy to kinetic and speed up as you spiral into the planet and crash. So there's weird cases where air resistance can actually speed you up. There's one of them. All right. Or what about a propeller, right? Propeller spinning, there's air resistance. That's what makes a propeller driven plane go forward. So there's, okay, whatever. Drop, rock, short building. Is that good enough?
Yes. I do have another question.
All right.
How does, let's say a repulsor or like a rocket, how does that push the object forward?
Well,
Isn't it pushing against air resistance, or what
no.
What is it doing? What is it causing to?
Come up here. Fundamental confusion. New York Times said the same thing and had to retract it. I got a medicine ball here. Okay. Grab it. Make sure. Throw it as hard as you can at me. Go. Did you move? Well, watch his back when he does that again. Do it again. Okay. Hard. Harder. Watch his back. Is he standing straight up or does he recoil? Ever so slightly, you recoil. If you shoot a gun, it's going to kick back against you, right? The idea is this. If you throw fuel out the back, you go forwards. That's it. Here's another example. Push on the wall. Okay. You go backwards, right? Right. If you throw a suitcase full of air out the back of your jet or out of your rocket, right, you're pushing some mass out. It's not much, but it's a little bit. Okay. So you push it out hella fast. That's why you don't stand behind a rocket thruster, because there's so much coming out. Got it?
Yeah, got it.
That's momentum. We'll deal with that in another chapter. All right.
Wait, so the denser the fuel, the faster a rocket should go, right?
I'll just say it this way. Chapter 9.
Okay.
We will get there. All right. Because I got to get through this crap today. It's awesome questions. And we can talk about it in office hours. I just got to do this now. All right. Absolutely. Hopefully that gives you a hint, though. Let's talk on the break. All right. What was the last one? Moon orbits Earth. Okay. Which ones of these are free fall? Is A free fall? What do you think? No. There's clearly air resistance is not negligible for an airplane. Do you agree? It wouldn't fly. How about drop the rock on a short building? What do you think? Yes. I would say probably free fall. And what I mean by that, free fall is okay model. It's clearly not free fall, but it's pretty close enough. There's going to be some air resistance. It's negligible. What if it was a tall building? What do you think? What's your gut? Free fall or not? Maybe. I would say maybe. It's less likely, but it's certainly good enough for this class, right? Right. The idea is, I'll give you a hint in just a minute how much it might affect this. How about the moon orbiting the Earth? What do you think? Is there air resistance on the moon?
No.
What causes it to orbit the Earth? So the moon is constantly falling. It just never hits, right? It's free fall. Now it's a weird case. You can say the Earth is in free fall about the sun. It just never hits. All right, so great. That's this term free fall. Now, regarding that, let me do this here.
Mr. Jordan,
Yo.
If the Earth is if the moon is falling onto the Earth is falling onto the sun should be falling onto the galaxy, right? Or
Yeah, probably.
And so then where's the galaxy falling into?
I don't know.
Like a black hole.
Remember, we could, I tell you what, chapter 13.
Okay.
I get to get out of stuff all day by pretending we'll cover it later. That's the move, right? Give me a second, Zoom. Yeah, but so basically you look at the center of mass, all the planets in the galaxy or all the stars in the galaxy, the planets are negligible. And you would expect that things are going to orbit the center of mass, right?
Right.
So, all right, and let me remember to do Zoom here. Are we seeing it? No, we're not. Wait. Sorry. Wrong one. That one. Zoom. I got to share screen. Let's do this one. All right. Those are good questions. Keep them coming. But it's just sometimes I will just be like, I got to talk about something else first. All right. So now look at this picture here. We've got a cannon here, and I want to point out, look at the angle and the speed just for a second. In particular, it's 85 degrees. I didn't use 90 degrees, which would be straight up and down, which would be pure 1D motion. The only reason I'm doing that is if it goes straight up and down, it's harder to see the line. So this would be like, instead of throwing the marker straight up, a 5-degree angle. Okay, not too crazy. Down here, here's the speed, 13 meters per second. When I run this one, oops, I'm on this one now. We would argue that this is free fall. Okay, 13 meters per second. Anybody have an idea about how fast that is in miles per hour? Does anybody remember a numerical factor to get from meters per second to miles per hour approximately? What's that? Okay, it's about 2.2. So basically, let's cheat and just double it. 26 miles an hour. Okay, so air resistance is kind of negligible here. We would argue, even though this isn't something that's dropped, it's thrown, this is still a free fall problem, all right? Now, in this case, let's do this and we'll run the time here. So right now, we see, oh, this was with air resistance. Do you see that?
Yeah.
So we've got air resistance in this problem right here. Okay, the air resistance, it said, this is, okay, fine. I don't really want to explain all the coefficients, but this is for a cannonball. They did some air resistance on that. Let's run the same problem again. And what we'll do is I may need to zoom out 1 unit. Sorry about that. I'm going to clear my annotations. Now I'm just going to take the air resistance off and we'll run it. And this will give us a feeling. Clearly air resistance mattered some, but let's look at the time of flight of these two. And I'm going to zoom back in here. Right. So in this case, we see that it added about 1/10 of a second out of, whoa. Come on now. Where is it? There we go. Actually, not even 1/10 of a second, but just, yeah, so somewhere around 1/10 of a second, let's say, out of about 3.1 seconds. What's 1 part out of 30 as a fraction or as a percent?
About 3%.
About 3%, right? You can remember it because 1/3 is about 33%. So 1/33 is about 3%. Anyway, so it's making a 3% difference in our time of flight. I hope you agree. Yes, there are differences. Look at the shape, but we're going to ignore that air resistance. Hopefully you agree that that's somewhat negligible. We're obviously making mistakes. Is everybody okay with that? Okay, we're only doing approximate work. In theory, here's a fun demo. We're going to give it a shot. What was I doing? I need to do this one. I probably need to zoom out. And I probably need to go over this way. Whoops, wrong way. Okay, there's a globe. All right. Now let's do this. So many buttons. All right, and I got to turn this. Oh my gosh, it's crazy up here. All right, so now you probably have heard about the coin and the feather demo. If not, read question 2.9 while I get organized. Read question 2.9. I'll send you a link later from this cool version at NASA that was doing. Am I on Zoom here? Where am I? Where am I? I need to go. Oops, I need to go just a little bit more this way. Sorry. Oops, other way. There we go. All right. So I don't know if it's going to show up on Zoom, but we'll do our best here. Okay, I gotta be very careful here. I don't know if you can see this at all. Take a look. This is just a magnet. This magnet is attached to a screw. Inside of here, you see there's like a piece of fur and a washer. See that washer right there? That washer is being held on by the magnet. And underneath that washer is a tiny piece of thread that's holding up that orange feather. Got it? Can you see it at all back there? All right. And so the idea is when I pull this magnet, they're both going to be released at the same time. Now, if there's air resistance here, which one is going to hit the ground first or hit the bottom of the tube first? Yeah, if there's air resistance, which one hits the ground first? The washer. Okay. If we could get the air resistance to be negligible by evacuating this tube, now, a funny thing sometimes happens with this demo too. What'll happen is the string will get stuck on the nut and then it won't fall at all. So hopefully that's not the case. All right. Try to get some of the air out of here. And again, what are we trying to show here is that if air resistance truly is negligible, free fall applies, meaning everything's going to fall at the same acceleration, the same rate. Okay. So that's what we're trying to show here. Now, because this demo sometimes fails, I'm just going to go for it. Oh, that was hard today. Okay. Here we go. Approximately the same rate. Did you see that? All right. If I didn't hold it up, we could do it again. But if you want to see it again, we can look at this on the break. The point being here is I'm trying to show you both with the simulation and with the real life experiment, if we can get air resistance to be negligible, hopefully the math I'm about to work out on the board, you'll agree, is somewhat accurate. That's it. Feeling good on that? Thumbs up, thumbs down. All right. And like I said, I'll show you a cool video later or something. All right. So, oh, here's another cool example. Oh, let me do it this way. Jeez. All right. Well, I have this medicine ball here today. Got a medicine ball, a basketball. Is this showing up on Zoom at all, Jules? No? All right. All right.
Basketball.
What's that?
Not so nice basketball.
Here, catch. Super flat.
Yes.
Yeah, it's like not inflated at all. Isn't this crazy what I have to do? It's all right. All right, let's try it again. How about now, Jules?
Okay.
Still good?
I feel like this is dangerous.
Yeah, it's physics. Is it still in? Okay. I'm going to try and drop these at the same time. Here, catch this. Watch out. This is serious. All right. Do you agree that's pretty heavy? Okay. Oh. All right. So you check the basketball. It's a real basketball. You check this. It's a real medicine ball. Which one of these should hit the ground first if I release them at the same time?
They're gonna be the same.
It's an interesting question. It depends how tall the building is. At this moment, this looks like a pretty short drop. Is air resistance going to be negligible or not?
Yes.
If we completely ignore air resistance, which one should hit the ground first?
They're gonna be the same.
Should be the same. If air resistance is non-negligible, which one would hit the ground first? The medicine ball, because it's more dense, it's going to cut through the air. 1, 2, 3. Pretty close to the same time, agreed? You can only hear one bounce. All right, that's enough of that. Let's get to work, right?
Mr. Georgetown,
Yo.
but isn't gravity mass times acceleration?
Okay.
And shouldn't the object with more mass fall faster?
Somebody just said something about chapter 5. You're asking great questions, dude. You're killing me, though. All right, so chapter 5 says force equals mass times acceleration, right?
Right.
Well, let's just think. We're going to learn that weight is a force, and that weight can sometimes be written as W, lowercase. You probably know that weight is m times g. I'm going to stick the vector on. Normally, you don't stick the vector on. Here, this just means the gravitational acceleration vector. So by this, I mean 9.8 meters per second squared. The direction of gravitational force is usually considered to be downwards, which is usually negative j hat. All right. So when you plug this in, if gravity is the only force, or if weight is the only force, wouldn't that mean that mg equals ma? What drops out? Got it? That's why the coin and the feather fall at the same rate. That's why the basketball and the medicine ball fall at the same rate. You're absolutely right. If you have more mass, you have more weight, you have more force. But it also takes more force to accelerate you.
Oh, that's
Right? It takes more force to accelerate a train than it does a beetle. Right? And so it's the same multiplier on both sides. Cool?
Cool.
If you have air resistance, since we're doing it, if you added in air resistance, usually high-speed air resistance is some constant times the velocity squared. That's why it doesn't matter much at low speed, but it matters a lot at high speed. Remember I said something about unit vectors in chapter 3 and how they're important? It's nearly impossible to code this and get a good answer unless you understand unit vectors. By the way, one of you is doing this tomorrow. All right, so, all right, anyways, we'll see how you do. All right, is that enough on that question? They're great questions.
Yes.
Okay. So yeah, I'm not trying to lie to you about this stuff being important. It just, sometimes it takes a while for it to kick in and see like, oh, there is actually used all that nonsense he's babbling about. Okay. All right. I'm going to leave. How many of you have done problems in 1D motion in the Y direction before? Just raise your hands if you have. Just keep them up. Okay. So I know we did a lot of problems in 1D motion in the X direction. I'm going to recommend very highly that you do problem 2.13 at home. Look at all those parts. Parts A through M. Okay. What I did is I split it up into very tiny pieces. Each part should be super short. So that's your review problem. I want you to do that at home. In particular, notice I didn't draw the picture for you. So with that problem at home, do every part, just in case you think you know something and it turns out you don't. And then check each answer one at a time. All right. And so I feel like we have to choose our battles. If we have time, I have 2 more lectures, this one and the next one for chapter 2. I want to make sure we cover everything. And so I'm going to let you look at this problem at home. We can talk about it. There's the old rule, 80-20. Right? In high school, 80% of what you do is in class, 20% is in class. In college, unfortunately, they flip it. 80% is outside, 20% in. That said, work this out at home. We're going to go for it. If I have time, we're going to come back and do more problems like this. So I think one major summary about this is the following. Just in case you need a tip. For free fall, we assume the following. We typically assume the following, okay? There's always exceptions, just like chemistry always has exceptions to the rules. Okay? Typically, we assume the acceleration is downwards with magnitude g. right? Now notice, if you remember from last time we drew these things, we had a delta x. Now we're going to have a delta y, v initial y. Check if I'm still on the board. I think I'm still good, right, Jules? Thanks. Okay. In this case, maybe you have some problem. Like, let's say we were doing the marker throw, right? Let's say there's a marker and it's going up in the air to max height. And it was thrown with some initial velocity, v0. Okay. And maybe, I don't know, maybe its height, maybe the height of this building is h or something, okay? Now, most of that stuff doesn't matter. I want to focus on one thing here. At some point, you are going to be doing this problem. You need to figure out delta y, v initial y, v final y, etc. In this problem, let's focus on these two lines here, v final y and ay. And again, we're talking about a problem where you throw a marker up in the air and it reaches some max height. In this case, what is ay? Negative 9.8 is a correct answer. And then if you say negative 9.8, what else do we have to specify? Meters per second squared. Excellent. So if we put the number, what is another way to say it? Somebody else. How do you specify it if I want to do it algebraically with the letter G? Negative G. I just wanted to remind you of this one fact. Remember, G is positive 9.8 meters per second. Shoot, I'm off, aren't I? Thanks. So remember that G is a positive quantity. Everybody remember that? That's like the most common mistake people make. So they know it's negative 9.8, and then they accidentally write down G instead of negative G. G is the 9.8. Negative is because of what?
The direction.
Say it again.
The direction of the positive.
Yeah, the direction shown is opposite the positive direction shown. Nice. Outstanding. Good. In this problem, when you get up to max height, what's the final velocity?
0.
0. Will the velocity always be 0 when you hit max height?
Probably, yeah.
No.
No.
It's only 0 if it goes straight up and down. Here's an example. Is the velocity 0 at max height?
No, because
It's still moving. Yeah. So I was deliberately trying to be sneaky. You're absolutely right. For a 1D problem, it's always 0 at max height. Agreed? It's when we get to chapter 4 and things go at angles, velocity is not always 0 at max height. It's always 0 in the y direction at max height. And I'm just trying to clarify that distinction now by okay. Yeah, go ahead. Oh, that's all right. All right. So far, so good? All right. Do that one at home. Watch out for that trick. All right. Let's move on. Oh, man. There are some hard problems on page 28 and 29. Some of them are easy. Some of them are hard. We'll definitely have time to come back and get at least one of those. But now I want to move on to plotting. All right. We've talked about one-dimensional motion. I know you've done some before. You could try some of those, use the solutions. I get some pretty sneaky problems in there. Page 31, take a look at it while I erase the board. Page 31. I'm confident we'll come back to those and do some more examples. Just erasing, Zoomers. Can't help it. I really like clean whiteboards when I start, so I double erase. Right. Go ahead and keep reading. I'm just going to get fired up here. Do a sim. You can talk to your neighbor as much as you want, or if there's something that's confusing there, talk to your neighbor about it. Get the sim set up.
I typically look at it. I was like, I'm done.
Okay, Zoomers, are you looking at my screen now? I think you are, right? Okay, thanks. All right. Let's talk big picture for a second. If you're going to be a scientist, you need to understand graphs, right? If you want to be able to communicate effectively with other human beings about technical information, most of the time that is done with graphs. Are these particular sets of graphs that fundamental to existence on Earth? Not necessarily. But this is the deal. We're going to start with these because they're, relative to some graphs, easy to understand. At first, it will seem insane that I just said that, right? But here's the deal. Let's pick some initial position, 4. Whoops. Say 4. Let's pick an initial velocity. How about -6? Let's pick an acceleration, 2. Now, to be clear, in this case, we can see on the board, I haven't hit play yet, okay? We can see here, let me just put a couple of labels here. The initial, whoops, in the x is less than 0, right? It's negative. Furthermore, we can see down here, a sub x is going to be greater than 0. When I hit play, what should happen? When I hit plays in particular, is this dude going to speed up or slow down? Slow down. You just told me the acceleration is positive, and yet the dude is going to slow down, right? On test questions, sometimes people screw that up because they don't see the picture. So it's important that we relate these pictures. All the time when you're doing questions with graphs, I want you to relate these pictures in your mind to these numbers. All right, so if I just play this thing and let it rip, we know the person's going to slow down. Eventually, what should happen?
Turn around.
Yeah, stop, turn around, and go back the other way. All right. So let's go ahead and run this. Oops. Not that exciting. This is exactly what you thought. Sometime he's going to hit the wall. Okay. Now, let's try and do this with charts. Whoa. Okay, let me clear my annotations for a second. Let's try and do exactly the same problem. 4, what was it? -6 and 2. And now, what do you notice about the scale here? These, I might need to actually, well, let's go back here. That's good enough. All right, I guess that's, shoot. All right, this one we could at least zoom in. All right, so now we'll hopefully be able to see these. Let's just run these and play them and then talk about them, all right? So in this case, we don't see the arrows. We just see this person moving around, going backwards, going to hit the wall. All right. And now, is there a way to, let's do that. All right. So I'm going to try and talk about these. And I guess I got to annotate so the people on Zoom can also see instead of pointing with the ruler. And actually, let's talk about this with the playback. Right now, the initial parameters are the y-intercepts. Do you see that? Look at the y-intercept of the position. It's a little bit off. Look at the number, right? That's off purely because of a numerical artifact in the simulation. When you round that, it's basically 4, right? They have to do some time steps in here, and so it gets a little bit screwed up when we do the playback. Look at the initial velocity. That is the vertical intercept of the velocity plot. And then the acceleration. What do you notice about the acceleration for most of this? Is it changing or is it constant? Constant, right? So obviously there's something going on right here. We could discuss that. Well, what was that? Do you remember? He hit the wall. When he hits the wall, you come to rest very quickly. In this case, that meant a large negative acceleration. All right. So basically, let's ignore the wall portion of this plot, even though it does kind of make sense. You can also see this. Do you agree this part right here is the wall? What do you notice about the position? It just sits still because you're at the wall, right? So let's kind of ignore the wall right now and focus on the rest. When I hit this thing, and let's go slow so I can actually talk. As he's moving, he's moving, he's moving. There's a special point at about, what is that? At about 3 seconds. Do you agree? Slowing down, slowing down, slowing down. I'm going to go right up to 3 seconds. Look at that. For a split second, look at the dude. See how he's standing still for a split second? That's the instant he comes to rest, reverses direction, and goes on, right? My claim is that your calculus class and this physics class, we're always talking about slopes, areas under the curve, tangent lines, things like that. All of those things that you learned in calculus class relate to this. Let's do this again. Let's focus purely on the velocity plot first. Okay, if acceleration is constant, remind me, what was the fundamental equation I told you relating acceleration to velocity? It was the acceleration vector was equal to what? Yeah, velocity over time, or dv over dt. In calculus land, what does it mean to take a derivative on a plot? It's the slope of which plot? Of the VT plot. Okay? So let's focus on the slope. In this problem, acceleration is constant, correct? So should the slope be constant or should it be non-constant of the VT plot? Look at the velocity plot. Is the slope of the velocity, ignoring the wall, is the slope of the velocity plot constant?
Yes.
That makes sense. Acceleration is a constant value. The slope is a constant. Okay. Now, is it the right constant? What is the slope on the velocity plot?
Should be 2.
Well, let's see. In this case, what is the rise? What's the rise? Let's go from 0 seconds out to 3 seconds. What's the
6.
rise?
Yeah.
I had trouble hearing you. Hold on. Say again. On Zoom.
6 meters.
Yeah, close. 6 meters per second because we're doing a velocity plot. Nice job remembering that there should be units. Outstanding. It's not 6. It's 6 with the units. Yeah. All right. So, and again, the units are right there. 6 meters per second. Nice. Well, what's the run? 3 seconds. So what's the slope? Yeah, I'm just gonna work it out. 6 meters per second divided by 3 seconds. So the slope is not 2. The slope is 2 meters per second squared, right? We're in a physics class. You're going to be annoyed by me constantly asking about the units. Do you agree that the velocity seems to correspond well to the acceleration and this fundamental equation up here, this A equals dv dt, right? So far, so good? All right. Now I need to clear these annotations. If you guys are at home and you want a screenshot, great. But remember, we're live streaming, so you can just go back and watch the video. 3, 2, 1, here we go. Okay. Now let's talk about the upper plot. How does position relate to velocity? Does anybody have any equations that relate position to velocity? Go ahead, speak up. I can't hear you.
Sorry, the position vector equals. I'm
Oh,
sorry.
Oh,
I
okay.
messed up. I was trying to do.
I
the
think you got it
arithmetic in my
flipped.
head.
You got it
Yeah.
flipped. Think about the units. The units help you. Do you agree we need a DDT?
Yeah.
So think, all right? We're going to need something on one side and something on the other side. We need a derivative equation. Which one is, yeah, think about the units. Does that help?
Yes.
Okay, so give it another shot. Or anybody that wants to. I'm sorry, I'm not trying to pick on you, all right?
Oh, sorry. No, it's the position vector equals dt.
So you said x equals dv dt. Check the units really quick. Does that look right? Just look up on the board, right? This is meters. This is meters per second over seconds. Is that going to get the job done?
Oh, no.
So then it's probably, you switch them, right?
Oh, I did switch that.
And so this is a cool trick. You can use the units to remember the equation because you're like, I know it's one of those. It's x and a v and there's a ddt. Just try out both and see which one works. So when I do it this way, do you agree it's got meters per second on each side? So that's the trick. You could use the units to check your calculus for me if you forget. Cool?
You were like trying to do the integral.
All right.
Yeah, I was doing integrals.
Oh, okay. We'll get to integrals in a minute. Slope of xt, right? So if we talk about this, if we're talking about velocity, that should be the slope of the xt graph. This one's a lot harder. First, tell me this. Is the velocity constant in this problem? Yes or no? Is velocity constant? No. The slope of velocity is constant, but velocity itself is not constant. Okay, so that means the derivative of x should be changing all the time, right? The velocity is not the same, which means the slope of xt. Is that sentence proven true by the charts you see? Does the slope change on the xt plot? We see a large negative, we see zero slope, and we see a large positive. Notice, we see a large negative velocity, we see zero velocity, we see a large positive velocity. We see that the slope on the xt plot does correlate to the velocity at any point. So far, so good? All right, now that one's a little bit trickier. One of the things that we'll do examples in a minute. Okay, this is just the fundamental understanding. Somebody said something about areas. You fool. Let's have to talk about it now. Let's talk about, let me do this. All right, I'm just going to do it on here. We will find out probably in next class that you probably know, well, let's do it this way. Gosh, A equals, let me just do it this way. dv dt, and I'm just going to be a little bit lazy here and just get this done. So acceleration was, oh, I used the wrong color. Crap. A is equal to ddt of v. And then just be patient with me. I'm going to leave off the vectors because I'm slow and lazy. All right. So we're doing one dimension. If you rearrange that, we get dv is equal to a dt. And I'm stopping the color coding because I'm never going to get done. If we integrate both sides of these equations, This means area under the curve. Under which curve? Which symbols are in that integral? A and T. Look at that integral. A and T are in there, so that's the area under the AT plot. Okay. In this case, what is the integral of dV? Say it again. It's not V. What's the integral of dV in calculus class? V is part of it.
V plus C.
V plus C. Or I'm going to cheat and say it's going to turn out to be, in this particular problem, delta V. Now listen carefully. If you integrate it, you're going to have to integrate from some initial limit to some final limit on both sides. And this is a common mistake students make. You know your teachers are always hounding you. You forgot the plus C. In physics class, the way I'm going to handle it is we're going to always do limits with integrals, so we don't have to worry about the plus C. But now think, if you integrate dV, you're going to get V evaluated at the initial and final. That's going to give you a delta V. I promise we will do that again in the next class. But for now, just does everybody see why we got to be careful? You can't just say V. You got to think about it. In this case, it's delta V. Did that make any sense? Thumbs up, thumbs down? Okay, okay. I could explain it more on the break too. All right. In this case, why is that so crucial to mention? Look, tell me, let's get green out here. Let's look between 0 and 3 seconds. I want the area here. What's that area? Notice it's important that I use capital A for area and lower A for acceleration. Otherwise, we're going to screw up big A and little a, right? What's the area? It's a rectangle. How would you get the area? Length times width. What's the length? 3 seconds. Yes, you remember the units. What's the height? 2 meters per second squared. What do we get when you multiply those two? 6 meters per second. My claim is that's the change in velocity from 0 to 3 seconds. Is it? Let's go look. Whoops. Here, V initial equals -6. What? Meters per second? V final is equal to 0. Is the change +6 meters per second? What do you think? I know I'm a little slow on the Zoom annotation, but I'm trying to do that so people at home can see as well as you. Hopefully that's making some sense out there. How about on Zoom? Is this making any sense to any of you? Or you?
Yeah.
All right, all right. So far, so good? Okay. Let's do this.
Mr.
Oh,
George,
yeah, go ahead.
I do have one question. That is, since velocity is the change in position, and since acceleration is the change in velocity, what is the change in acceleration?
You jerk.
Fork.
That's the name of it, jerk.
Oh,
DADT is jerk. Yeah. No, I mean, that's chapter 22. No. Yeah, that's called jerk. And then if you're crazy and you read Wikipedia, you can say, well, what's the derivative of jerk? Snap. What's the derivative of snap? Crackle. What's that? Pop. Whatever. At some point, yeah, you could go read those. Dom, am I making this up? No, it's just dumb, but it's fun, right? Now, to be clear, jerk is actually pretty useful, right? Because think about it. When you sit in your car, is your acceleration constant? Probably not, because you're going to step on the gas, hit the brake. There are going to be changes in your acceleration. And so oftentimes we might want to understand that jerk, that change in your acceleration. So it's aptly named. Good? Now, that will be later. That I promise we'll come back to that. We'll probably do a problem on that in the next lecture. So we're getting closer to it. Yeah. Good? Now I want to clear these drawings. 1, 2, 3. Here we go. All right, let's talk. We're almost there. There's a couple more pieces, and we'll take a break, and then we'll come back and do some problems. So just hang in there. We've got about 15 more minutes of this battle here. We just talked about the area under the AT curve. What would be the logical next thing to talk about?
Area under VT.
Unfortunately, yes. So V is equal to dx dt, right? From that, the analogous equation, you could cross multiply, and you could say that dx is equal to v dt, and we could integrate that, right? Again, we're going to stick on limits, initial and final, initial and final. Okay, on this side, that's going to be the area under what? Under which plot? What symbols are inside that integral?
Oh, under the velocity.
Yeah, under VT. Good. And on this side, what's that going to be? The integral of dx is? Yes, change in x, delta x. All right, so far so good? Okay, you ready? Let's do it. I need some help, people. And not just with the math, but we'll focus on the math right now. All right. What's the equation for that area? Area equals half base times height, right? Okay, help me. What is the base? 3 seconds. Excellent. You're remembering the units. I love it. It's always frustrating when students do all the work right and leave off the units, and you just have to mark them down and just be like, well, you're wrong. It's not fun.
I'm not a student.
Well, hopefully you won't be, because you're doing it right now. So let's keep it going. What's the height? I like that. It's a function. The height can be negative with a function. Outstanding. What do we get for the area? Wait, was it -9?
Oh, no.
Yeah, the half. All right. So my claim is, what is x initial? What was x initial in this problem? 4. If you recall, right, we're ignoring that little rounding error there. Okay, 4 meters. What's the final position here at this time? -5. Is the change -9? Woo! It works. Does that make sense? All right. Okay. So far, so good. Jules or Dom, do you have any comments you feel like making at this time? Or are you good? You're good. Dom, you're also good right now? Okay. Just checking. Any questions from Zoom? Or anybody? Any questions from anybody right now? Yes, go ahead.
So if I remember correctly, I think when we were talking about the integral of acceleration
Yes.
or the derivative or whatever, it was torque. Or I know torque was the integral of something, and I can't remember what it was. I was wondering if torque and jerk were the same.
No, they're not the same. So jerk is the derivative of acceleration, and torque is chapter 10. Woohoo! I'm free. So I promise, torque, if you look in chapter 3, I did some torque problems. If you want to look, the definition of torque, it's a common cross product problem. So that's why we're going to wait for a little bit. But if you care, you can learn more about torque on page 69. And it's defined there, and I work it through. Is that cool? The definition, we have to, it's a long definition, and it takes a lot of understanding. So for now, we could discuss it more later. Is that good?
Yeah.
Yeah, page 69, if you want to learn about torque. There, yep. And torque relates to angular acceleration, which we haven't talked about either, and pivot points, which we haven't talked about either, and forces, which we haven't. Yeah, so okay.
George, I just noticed something. The acceleration when it hits the wall, when it turns negative, it doesn't.
Okay,
it
wait.
goes past
Let's catch up. Let's make sure everybody knows what you're talking about. He's saying here, do you agree you have a large negative acceleration vector, right? That's what you just said. I'm just making sure everybody on Zoom can also listen to your question. What's else?
So why does it go past -2? Shouldn't it just reach -2 and then go to 0, since -2 would cancel out the previous acceleration?
You can have, I could accelerate 5 meters per second now, -200 meters per second the next second. That's totally fine. And in fact, if you run really, really fast and sprint full speed into a concrete wall, that's exactly what's going to happen to you. And that's what we watched, right? If you run into a wall, it takes almost no time to stop. Clearly, your acceleration must be bigger because your velocity is changing so rapidly.
Oh,
And that's why you get injured. If you're in a car accident, right, you can accelerate from 0 to 60 in like 10 seconds. You hit a concrete bridge, you slow down hella fast and you get injured. When you have large accelerations, you're going to get injured. This seems reasonable. In this simulation, the person was running into a brick wall. They should be stopping hella fast. That means their acceleration should be very large. Now, to be clear, that doesn't necessarily imply it has to be negative. In this particular case, we need a hella large negative acceleration because the person was moving forwards, or positive I hat, and they need to go from a large positive velocity to 0 quickly. Think about it. Look at the velocity plot. When you hit the wall, your velocity goes from big positive number to 0 almost instantly. You need to have a large negative acceleration because you have a large negative slope on the VT. Is that good?
yes.
Outstanding. So it actually makes perfect sense. They're trying to model the stop like, oh, you just stop almost instantly. Okay, good. All right. Now you heard me say things like moving forwards, speeding up, slowing down. Okay. This is probably one of the things that drives me nuts because people, I'll write these words in questions and assume people understand them, when in reality, unless you practice, you will screw up moving forwards and slowing down. In particular, look at the bottom of page 31. Look at the bottom of page 31. By the way, everything that we've just said is on page 31 so that's kind of like your summary of what we've just been talking about. Page 31, all those bullet points talk about the slopes and intercepts and things like that, okay? But at the very bottom, I want you to remember this. Speeding up, A and V have the same sign. I do not want you to think about speeding up as acceleration is positive. I do not want you to think about slowing down as acceleration is negative. I want you to think of it this way. Speeding up, A and V have the same sign. Slowing down, what must be true? A and V have opposite signs. Because that's so important, we'll write that down. I'll put it on the board in a minute. But I want you to watch this simulation and see if you agree with that. I'm going to clear the drawings. Ready? 1, 2, 3. Okay. Let's go through this. In this region, what's true about the velocity? Is it positive or negative right here? It's negative. How about for this region?
Positive.
V is positive. And how about for this little region? Is the velocity positive or negative? It's still positive. Okay, now let's do the acceleration. Over this region, the acceleration is positive. Over this region here, still positive. And on this region right here, okay, so tell me now, for this block of time, is it speeding up or slowing down? Slowing. How can you tell? Opposite signs. Over here, like speed up. And then right here, this last region, slowing. Why? Opposite signs. Not because A is negative, it just so happens to be negative. All right, let's watch it and make sure you believe that. Ready? Slowing down, slowing down. They're opposite signs, opposite signs, opposite signs. Oh, come on, that's too well. Now it switches, speeding up. We're seeing the motion speeding up. Rapidly slows down. So rapidly you could barely see it, right? Okay. Feeling good on that? Okay. Let's get back to normal. And then it's almost break time. I just want to make sure we clarify, and let's look at page 31 carefully, everybody. See if there's any other questions you have on that while I get Zoom kind of back to normal here. And get these screens up.
Why isn't the area under the XT graph?
That's an interesting question. There might be some use, but I don't have something off the top of my head for you. So I guess you could try and think about what the units would be. That's one way to think about it right away. What would the units of the area under an XT plot be? If you did an integral, so the question was, what about the integral of x dt? So my first claim is, I don't know of a use. That doesn't mean there isn't one, but I don't have one, okay? So the integral, what would the units be? What are the units of x? Meters. What are the units of t? So what do you know in the real world that has units of meters times seconds? It's not something immediately obvious to me. That doesn't mean there's not some use for it in some weird application. Cool? Yeah. And maybe you could simplify some more complicated problem to something that relates to this integral. So, but again, I don't know something off the top of my head that has these units that I could think of that I would care about. Cool? Yeah. Dom, do you have any comments on that? Yeah, just because you can do something doesn't mean it's useful. Yep. All right. Kind of like me. Just because I can stand up here doesn't mean I can teach. All right, let's keep going. It's all right. That's all right. Let's see. Let's focus on this. There was something I wanted to say and write down. Remember. You should write this on page 31. Right at the bottom there. Okay, if A and B have the same sign, what was true? Was it speeding up or slowing down? Speeding up. And maybe I should be clear that we're in one dimension, right? Let's do this. I apologize for putting those vectors on there. I'm going to say it like this. If A sub x and B sub x have the same sign, just because that's more appropriate for one-dimensional motion. If we talk about vectors, it gets complicated because the different components could have different signs, so I apologize. And maybe I'll clarify this is in 1D motion. 3D motion we could handle with a code or something. Let's throw in one more. If the a sub x, or the acceleration component in the x direction, is 0, what else do we know? Yeah. So what has to be true for not moving at all? How do we say at rest? If what? If no, if v sub x equals 0 at rest. Now you might be saying, wait, don't they both have to be 0? You could argue that if you want to be at rest for an extended period of time, absolutely. Remember in that simulation, we saw the guy just for a split second, right? If we're at rest for a split second, you could argue that you're at rest at that one instant as well. Cool. So think about this. Right at the top of flight, you could argue the marker is instantaneously at rest. Obviously, this happens for less than a nanosecond. So is it that useful to consider it that? Yeah, but whatever. So maybe if you want, you could say instantaneously. Good. All right, it's been an hour and 10 minutes. Let's take a break, come back, and we'll try and apply these unless anybody has any questions about any of this crap on page 31. Is that a good review from your calc class, et cetera? Hopefully. We'll find out, right? All right. Zoomers, any questions out there? All right. So we've just been shooting the breeze here on the break. It's about time to get going again on Zoom. But yeah, we were talking, I was saying that there's a lot of work in this class, but basically once we get done with about chapter 10, then you can start to do cool stuff with your knowledge, right? And you can start, right? It doesn't take much to start doing really cool applications. That said, I feel strongly that it's important to just hammer the crap out of you guys on this stuff so that you're excellent at it. That way, this is not what's holding you back. Because if you have the first 10 chapters super solid, you can pretty much learn anything without too much pain, right? But yeah, so it's crucial that you're just like expert at this stuff. And there's gonna be times when you're just bored because you're like, I don't want to be an expert. I want to have an A and get paid 6 figures. But I feel like this will help you long term. And you probably hate me and be bored with me, but if it means you get a better job later and can cruise through junior and senior year, that's worth it to me, right? So it's also tricky because everybody in here is a different major. And so there's definitely times where I know I'm doing something that's helping these 3 and the rest of the class is like, this is dumb, and they're right. But then there's another day when it might be something for you and it's dumb for them. Yeah.
Why is Don sitting in?
Oh, so we are working on a grant, and as part of that grant, actually that grant is what pays for Jules to be here, right? And as part of that grant, Dom has paid himself to sit through my lecture, and we're trying to improve our consistency between our classes. So the only way you can really do it, like we could talk about it, but if he just sits in here, he just kind of is familiar with the kinds of words I use and the terms I use and the pictures I use. So when he's teaching, he could be like, remember when you did this, or remember, right? And so we're trying to improve our similarities in communication as a program. And so imagine how boring that must be for him. I mean, he's back there grading, right? So, but if he just sits in here and he's picking it up, right, there's times we'll be like, oh, I discuss it this way, or I discuss it that way. And then that gives us something to talk about later. Yeah, I should probably be sitting in on his too, but I got kids and I got a life and it's tough. Yeah.
Back to what you're saying about the first 10 chapters.
First 10 chapters, yes.
Like algebra that I got to learn really well.
Algebra, calculus, yeah. Go ahead.
How come we can say about 163 to 162?
Oh, well, so again, that was my claim is once you finish about the first 10 chapters of this, we feel confident you could learn 162 or 163. Jules took 162 before 163, right? And right, do you feel like you were able to learn 162 just fine or 160? Right? It doesn't really matter, right? They weren't that related, right? Yeah, there's a few little pieces. If you take 163 before 162, you better understand electricity for a few chapters. But if you take 162 before 163, you better understand thermo and oscillations, right? So there's 1 or 2 chapters that they're kind of overlap, but other than that, you can just kind of get through it. We want students to get the hell out of here and get jobs, right? So, right, and because we're a small school, we can't offer every class every time. So if we had to take them in order, that would affect the way we teach them. And now, if you fail 161 and have to retake, you don't get screwed out of 162 and 3, right? So it's like, this is the filter class. Buckle down, do extra work for this class, and then you can just struggle through the other ones and make it. Yeah, it's a strange system, education, right? But that said, even though most of education is kind of total nonsense, I feel like you're at least getting some useful skills here. What were we trying to do today? Understand how to read one type of graph. It's like learning a language. If you get real good at learning one language, you can learn others more easily. So if we get good at reading these types of graphs, some of the principles apply, like checking the units. What is an area? What does a slope mean? Thinking about it. If you can learn that, that will help you in many types of graphs that actually help you get paid. So yeah, I feel like some of this stuff is kind of useful and universal. That's this topic. That's why I kind of rushed through it. Yeah.
I've been like staring at that equal ever since last semester.
Yeah.
It just balances out. Is it like magnetic or how does that?
No, this is chapter 9, right? So it's just center of mass. Look at this thing, right? They put some weights out in here, right? So there's some mass here and here. There's some mass here and here. The center of the mass is, take a guess where? The beak. if you want to do something similar, get a 50-cent piece and 2 forks. And well, people used to go to restaurants. This is what my parents used to do. They'd give me a 50-cent piece and 2 forks and say, balance it on the edge of the cup. Same idea, right? Get the 2 forks this way, the 50-cent this way, pivot point. Chapter 9. Good enough? Yeah, it's just an old center mass joke. Okay. We ready to do some problems? All right, so here's what I'm going to say. Do problem 2.25 or 2.26. And then I think one of the, oh, it's 2.27, excuse me. So there's a, look at page 32 and 33. You see the plot on page 33? That plot goes with question 2.27. I know that's not perfectly clear. If you read the question in 2.27, it says use the plot above. So depending how spicy you're feeling, try question 25, 26, or 28 and 29. Do it. Go. All right. And Jules and I are going to start circling around and helping you out. And Zoomers will try and check in. So basically anything off question 32 through page 34. If you think you're the shit, try page 34 first and see if you are. If you're maybe medium level, try 2.27. If you're really bad at this or forgotten a lot, try 2.25. You choose your own adventure. All right. And I'm going to circle. So there's going to be a lot of boring white screen here. Zoom, I promise. Jules and I will check in on you occasionally. All right. Remember, you got the solutions. I'll open up the laptop card. If anybody wants a laptop with the solutions on it, if anybody needs a graphic calculator, or not a graphic, scientific, I got that. Couple anyway. Guaranteed going to be a graphic question on your first test. Usually I have a graphic question on every test. That's my philosophy. So just in case you're wondering, is this going to be up? Yeah, hell yeah. I love this stuff on testing. Every year, you look at every test, I've always got a graphic question. So be excellent at this. My passion that you learn how to read and interpret graphs. Talk as much as you want. If you want a laptop, let me know. Then at the end, try to get the right slot, etc. If you get stuck, don't be shy. Talk to us or look at the solutions if we're not right there. Right? This is your first problem. Use those solutions if you need it. Oh, no wonder. You guys need one too? Talk as much as you want, right? You suffered through the first half. Now you can relax a little. So, get you guys complete. You got one. My bad.
the same. Same. Actually, no. I can do it. No, I'm asking. you to do it. This is the last one. No, I agree with this. Oh, it's okay. How did you get that? I was just using a small. I was going.
Yeah, it's easier.
No, I see what you do. There's an attachment to it, but I don't know. Yeah, that's.
It's for now.
Right.
Okay. Well, it works great, right? So you just gotta scroll. Somewhere? Yes. All right. Checking the answers as you go. Don't forget to check the answers as you go, all right? Get something.
I know.
What? This is chapter 2. Yeah, remember there's that whole stupid 2 thing. What were you saying?
I'm having an issue with this one, but if I keep staring at it, see,
Left and slowing down.
so that's what velocity is like. So if I stare at this, I'll be at further. So, so I was trying to figure out. Oh, concavity, no? Ah, thank you. I appreciate the help.
All right.
Are
Okay, we got the solution somewhere. Go back.
we ready?
What's up?
I mean, yeah, that's true. I was saying it's about this because see how this isn't exactly on the dots? I was doing, that's why I put it down.
Just estimate. Read the graph and your base is 2, this is 3, so this is. So. It's kind of eyeball it. So it's not. Typically what happens is these are the few problems in class where you see it and see it. So I don't expect you to get the same number of items. I expect your answer to be within the ones, yeah. Reads the plot is always gonna be a little bit different. So, but right here, these are nice books.
I got because this is concave down, so that would mean that.
Okay. Okay. Is that good for now? Okay, good. Get somewhere? Okay, okay. Okay. This has to be since this.
Yeah, I was thinking,
Yeah, it's a little bit easier to read there, so you'll snap a picture of this and plot it on your phone. Yeah, well, I mean, this is. Yeah.
So you said it's below it.
Yeah, exactly. It's more for each work process. So anytime you did, that was one of the specific things on this problem. I wanted you to have to read, I wanted you to feel it on that. See it. Real world.
I don't have any.
That would be, right? Yeah, obviously, yeah, so you got some points there. So you're trying to get part. Okay.
There's a point of question where I started to go back to concave up, it's at 0 and now it's
So,
equal to.
not gonna be exact. What is it referring to? You're doing a graph. Graph problems don't kind of do the same things. Usually, most graphs can be read to about 2 seconds, which usually.
The inflection points here.
Trying to read a graph.
So this is concave up right here.
So, expect your answer.
But it's
you
not,
can do it,
right?
but expect that you're not going to match your weight. The third sig fig.
Oh,
You guys match
oh, you're right.
the second sig fig, but maybe we'll have 1 or 2 or 7.
Oh, I'm thinking positive, negative.
But this is where like you were.
You keep everything in my head.
Because I'm right here, see, I was like, like the cooking.
You're like, oh, yeah.
You're like right up there, like.
That's why we compliment.
So you have,
Like, we don't.
Like, in fact, if you do the
I have,
math,
do you understand the overall concepts more?
40%.
I get
That's not excellent.
yeah, I'm very bad at it.
That's
Which I should probably improve if I'm
just
not
because it's on these. You're going to get something. Something that's easy for me to find.
I miss it.
I need to.
My calculus teacher sucks.
I like I have
Chris?
three of my friends who are in Calc 1 with my
Right, like, we don't want to use.
I want her to teach all of my classes, I swear.
Otherwise, you can do way off.
when my
That
hot
means I'm kind of
teacher,
bullshitting the
he
numbers.
used to be
And that's where
her,
to
one of her high school, she used to be her
Somebody else
high
might say 2.6, somebody else might say 2.8.
Oh, really?
Yeah.
Oh, that's right, because she used to teach at.
Like when I see this
Right?
blown up, maybe it's.
Yeah,
only
Hey, did you hear
2.2.
about that?
I don't know.
No,
I was thinking about.
This is exciting.
bro, I don't
So-
know. Half of the stuff that happens over here.
Yeah, so you could do this one,
What
this
happened
one,
was
right?
the
So you
cheerleaders.
could do this point
This is
to
on
right
my-
there. That would also,
Let me show you the part.
but then notice you're gonna have trouble reading
I don't think I
that.
saved it. But I have a
Basically,
video.
you wanna
Anyways,
pick at least,
so the
you wanna pick
cheerleaders
two
were
grid
like
lines, right? So either have the horizontals or the vertical line on the grid, and then the other one just sucks.
basically what this
So you
is
just
saying
do it
is
in a row.
that
You see what I'm
the
saying?
cheerleaders caught
Yeah.
the vice principal and the JV boys
Okay,
basketball
it's
coach
a
and
mic.
all this. Kind of. They're just- Anyways, so that's like a big scandal right now. Here's the video. Here's the video.
So it's typically on a that's what I'll say is for this problem. you don't need that. So for this problem, I put it in just to have.
There she was, there she was a picture of like guy getting.
That's all.
He one of the steroids from high school.
It's not even that interesting.
He always wants to.
So they were like showing like steroids, but there were like a few steroids.
What's your name?
So everybody.
So you probably want to do it also, get that 10,000 instead of like-
Yeah, no, literally, I was at CSULA, this is my cousin. I was just chilling with some friends, and then we were walking to the basketball. CSULA, Kelsey, LA. It's kind of like,
They do it
no,
around.
CSU. No, but it's Cal State LA, and then I was walking to the basketball courts to the dorms, or from the dorms, kind of like going towards the apartments. And on the way, there was like a party on the way, and there's, it was like very troublesome. I was like, why? It was 3 in the morning though.
I mean, that's fair.
Everyone was acceleration is negative.
Well, I'll show you.
Yeah.
What
So
I did
that's-
is I just looked at this one for definition of fun. So we're going to use this point.
Wendy.
We're trying to use this point. Basically, we're gonna use this point. This its addition would be two. So the up and down to the guy.
Okay, let's make mental notes first, so we don't keep getting back confused. So conjugate
Next
down
orbit is how much the right. So it's
equals acceleration is negative. Conjugate up,
This is 2, this is 3, this is 2.
acceleration is
That's how you would get. So you follow those lines.
wait, no, this is, I don't want. I would have to do it for all of them. Yeah, I know.
Like, yeah, like chunk it down. Like, right, like chunk it down.
What do you think? Did someone?
That's good. I'll figure it out. Hey, listen time.
So was part C, the area under the BT2. You got that,
2
right?
and 4.8.
So remember, what does the BT curve mean? You got it, Jules? Thanks.
Yeah.
What's the area under the BT curve? Displacement, change in position. Excellent. Look. remember, what is the physical meaning of displacement? It means a change in position. So if you know the initial and you know the change, you can figure out the final. I read something else. Area of the mass, right? This is the area. What do you think? Get somewhere? Where are you going? Eat? Okay, let me show you. Can I borrow your pen? Yeah. Okay. Look at this. What are we trying to do? The slope at 3 seconds. Slope, I mean, right? Like you're trying to drive it. But remember in calculus, or some math. Remember I don't use it.
Wait, what are you looking for? E? Oh, for C, moving left and speeding up. So the velocity
Remember, that's gonna be something like.
and the slope is negative. So
Well,
velocity
this
is
is
negative here.
that's xt. So instead of y x, normally it'd be like y final minus y initial over. Like here we need x final minus x initial over t final minus t initial.
No,
X is
just from
like
5 to
the y
6.
T is like
Because the
x.
velocity has to be negative too.
But it's increasing.
Agreed?
Yeah, but here the velocity is
So we need 2
constant and the
points.
acceleration is
Oh,
negative.
yeah. Yeah.
Here's the point I care about. Let's get one just before. going
I'm like, like
Wait, what
here
do you mean from like floating?
Those 2 points.
from
That means you gotta
4.8.
remove the values off the bar.
No.
Bars, and just estimate.
Why would it be from 4.8?
And that's all written up in here too.
Doesn't reach out yet.
Oh, sorry, from 4.8 to 6. Yeah, you're. See, that's why I need you because I can't see.
That's what I'm doing right there. But help. So here's the deal. This is like our first problem. Lean on the solutions heavy.
4 to
And the
6.
second one, try to not lean on it. If you get stuck, lean on it again. And then eventually, at some point, the solutions, stop using it. Try, and then we'll be about ready to do test questions where you don't use the solution at all and see if you actually do your shit. Cool.
Where's my?
So, yeah, just because it's more important at this point to read the solution, learn from it, and ask me questions. If the solution doesn't make sense, I'll help you too, right? Because I'm here. Cool? Yeah, so lean on it super heavy right now. I think, get somewhere?
Oh, yeah, we're good now.
All right, that's good, that's good. Okay. You guys can go on to 2.29 fractions. Those are both good, right? So typically I either do an XT or a BT plot on the text. Right? And so I'll ask some subset of these questions.
These are good questions.
Yeah, they are.
Yeah,
I'm like
here's
thinking.
$50 out of it. Right? I'm hoping, I tried to put in the same kinds of tricks I would put in on test day, on those two. In fact, I think those were both old test questions that people sucked at. So I
Oh,
just put them
really?
in the book. That's how I write these books. It's just, here's a test question everybody failed. Here's a test question everybody failed.
That's fine.
How long did it take you to write?
10 years,
10 years.
15.
Both of them?
Yeah. So it takes a long time. Figures take a long time. You'll learn this week and next week when you have to make your own presentation. It's like making a graph. It should only take 5 minutes. Next thing you know, you look up, right, Jules? It's like you look at these presentations, it should only take 5 minutes. And then because I actually care how they look, it's going to take forever.
Yeah.
But you get faster at it. So that's why we're doing it 3 times. Once you leave my class, you'll be able to make a presentation in an hour if you school. If your teacher says, you need a presentation tomorrow, you will go. Wait a minute.
I got it. Well, except for these two, right there, it says moving left.
Moving left, what does moving left mean?
Yeah, it's going in the negative
Maybe
direction.
determine what is negative. Position negative, acceleration negative. When you say moving left, what is negative? Velocity is negative. When you say speeding up, oh wait, which one did you say moving left and speeding up? And moving up? Okay, let's just start with the first one. If I say moving left, speeding up, Moving left tells you what? Velocity is speeding up, then tells you.
Acceleration is positive.
So the acceleration is the same sign as v. What sign was v?
Negative, so therefore acceleration is positive.
So tell me,
Did you
is
get
there a
negative
point in
eight
time
years?
where velocity is negative? And acceleration is also negative?
No.
Sure. Now go the other way. Is there a time when you're moving left and slowing down? What's this moving left mean?
The negative velocity,
Okay, what does slowing down mean?
positive acceleration, good, the opposite.
Okay, good. So in this case,
Yes, so that would be 0.02.
that's it. So then obviously one of your
Negative
others is
or
wrong.
positive?
Right?
yeah.
Okay. It gets tricky because you
How
know,
did she get
right?
40?
The rules that we use for XT graph are not the same as
For-
VT, but they're related, right?
Right.
So just, right, for the velocity, what are your, right, anything below the time axis is moving left. Anything above the time
I
axis
got
is moving left.
20.8.
Over here, that's not necessarily true. X is below the time axis, but you're moving forwards, right? You're going towards more positive X. So the rule, yeah, is that good?
Yes, that makes sense.
Good, good.
First.
What do you think? That is somewhere? Good. Okay.
Oh, I see.
Are you those? Arbitrarily. Could someone else have chosen different points? Yes. Should our answers be approximately the same? Yes. So that's the deal. But now, if you had chosen that, choose this point right here, it's easy to get the numbers, but it's hella wrong. It's not even close to the right slope. So unfortunately, in reality, when you're looking at the graph, you're trying to get a slope, you do not want to pick points far away. You want to pick points directly at the top of the entry. That's why I chose these. If you had chosen this one and this one, I'm cool with that. But at some point, right, anything else past there, you're estimate. So it's literally just do rise over runs, leave up with some flat that are close to the point you care about. And don't pick points you're close to the point you care about, you're wrong. Is that?
Yeah, yes. Because I was trying to make it easier, so I don't know this.
Look at this. Let's say I want the velocity at 4 seconds. What about from here to here?
Yes.
It looks good. It's 40% off. 40% good. Like it looks, that's the thing. You
Yeah.
think, right? You think, yeah, that looks close. I assigned that. Every student tried to do that. I'm like, this is so awful. Why are you doing this? And I realized it's because I didn't tell them not to do it. I'm like, all right, I guess I better tell you. So that's why it's in the book. But isn't that surprising how much you're off?
Yes.
Yeah, yeah. Yeah, so points close to it, right? When you're getting slopes, get points close to it. Right? Yeah, I was shocked when students did that, but I didn't realize it looks good, but it's not. Yeah, okay.
Negative. I know that from here to here. The velocity is slowing down. That means that the acceleration.
Shortcut. How do you get from X to acceleration? What does the second derivative mean? X to one. Not slope, but. Concave up. Concave down. Remember that? Sort of. There you do. Yeah. Yeah. I don't know how many- Cool. Yeah. Right. So that's one of the things I forgot to mention. Okay. Yeah, I should have talked about that. Where's my phone? How are the Zoomers doing, Jules? Not many questions, I'm assuming? All right, that's cool. At least you're getting something. All right. Oh, question back there? Yeah. Look, the area of this.
Do you get 24.8?
So
Yeah. Wait, I got 25. Did you add them? 6.4 and 14.4?
Yeah, I was just, I just had it.
I know I can do this problem. All of the tricks that you need to improve my students' problem. You want to make sure you understand.
Well, no, I'm on the challenge.
Go back here, go right. Oh, that's the simulation we already did. Actually, if you go there, I can apply it to it. Took down
Good
something.
job. Okay, I'm done for the day.
So, but if you go to the 160 workbook. So that tells you, that's it. So it looks like I need to change the number. 6, so it's like so. But if you want to kind of play around with it, this gives you ideas on how to make simulation. Like, that's what we're doing. So,
What's the date?
yeah. But since we did that already, I would say try to.
Already doing
Yeah, look how pretty, that's got part P. Oh my gosh, that's insane. This one. Part P is pretty hilarious, right?
You wrote this book, why is it surprising to me?
Oh, I just forgot. That's like one that I threw out because it's too long. Anyways, all right, you doing all right?
Oh, how do I check the date?
Are you guys doing all right on those, that second problem? The
I finished.
Nice.
Yeah, I'm just gonna check my answers.
What do you think? Getting somewhere? Yeah, you're making a chance.
I forgot to label the A's.
Sometimes
Oh, I
people try to be too pure. The other thing works out, but let's do it. I appreciate it. Yeah, just right. The area is the change. Right? So if you know the change, can I write something down? Okay. That's the area.
So it's gonna be what's this gonna end up with?
Yes. What does X mean? X line is exponential. So because you know this, and you know the area, you can solve that. That's all I'm trying to do. Does that help? All right, all right.
Wanna know something what I did?
What?
I got all of the math right, but I didn't put units.
Yeah. So I'm glad that you actually remembered that that would be points off, right?
Yeah.
So that you correct your work, and as you get in the habit of correcting yourself, then you won't screw it up on test day. Yeah. If you finish your test early, what's the thing you probably should do then?
double
Go
check.
through every single box and make sure, did I write units or not?
I made that a habit.
Okay, yeah, so you'll
Double
probably.
checking.
What's that? For the first 4 seconds, right? For the first 4 seconds, is acceleration constant? Do you know any equations for constant acceleration motion? No. That's true for constant velocity motion. If you have constant acceleration, give me an equation that's related. I think you can change in position. You said change in velocity, but yeah, the delta x equation, right?
Yeah, for position, yeah, it wouldn't be.
Well, if you use, here, let me give you a trick. You know what to do. Watch this. You agree you could write an equation x final equals some shit?
Yeah.
You agree you could write an equation v final equals some shit from kinematics? V final is v as a function of time. X final is x as a function of time. Got it? Did that help? And that's actually foreshadowing the next lecture. Where we do the separation of variables and we'll dig into this calculus in more depth. Good? And all you got to do, so basically, if you identify x final as x is a function of time, you agree? You tell me the time, we get the x. If you tell me a different time, you get a different x final. So clearly, x final is x as a function. Good?
Yeah,
Yeah. And that's why I asked it, so that you would be like, oh, that's it. Now, that only applies if it's constant acceleration. If it's not constant acceleration, I guess we need the next lecture still.
yeah.
Right? Right? That's why we got 3 lectures on it. You're good for that, right?
Yeah, I'm good.
Good. What about you? Somewhere?
Yes, right now just calculating. Split and acceleration.
Yep.
But I didn't realize that you could do
Yeah.
kinematics equations.
Oh, okay. Now, I'll say this. This problem has been done many, many, many times. Not to be an error.
This is my
Pretty well. So
favorite.
what do you think the error is?
I use it for work, school, I use it for every class. I only take this one.
And it's like the, I update the.
Yeah. The 0.5 is pretty.
And that's what I throw in.
It's bad form. I would say it's not complete. It is.
Yeah.
Something happened. You maybe should resize.
What did I say?
I heard ass.
Oh, no, I think I said pretty nice.
Oh, you said pretty ass.
So it's not incorrect, but it is bad style. And I'll give it.
It's 172.
For pencils, I like places.
Yeah, for pencils, 172.
What the?
So like for pens, you just fix it.
I agree. But you agree?
I want
Yeah.
something to
Yeah.
eat, but I don't know. Oh, I know it. I want Chinese.
So tomorrow.
Oh, it sounds pretty good. I never go there. I went there on the first day of last semester, like as a good job. No, but I went by myself. And then after that, I haven't gone there.
I thought it was pretty good.
Yeah, no, I love Wingstop. I just never go.
I went on Monday with my friend.
Hey, equals
I like Buffalo Wild Wings, but I think Wingstop is better for like most flavors. But I like Buffalo Wild Wings for what's specific.
Yeah.
The Parmesan garlic.
Oh,
Is wet.
I like that in the Nashville hot.
It's a 10-pound
I have
force on
never
me.
tried that. I don't do well with spicy. I can't even eat tacos.
Right, so that's
Do you
why
think
it's
orange
something
chicken is
spicy.
They can make it spicy, but if they make orange chicken spicy, it's general chicken.
Because I know my little cousin just regular orange chicken.
They're weird.
They're just weak.
Do they not eat spicy food? I thought that was the part. My favorite is spicy ass chili on your head.
Bro, some chill like this. Good job. I know what you want. You're gonna go to Canada.
Yeah.
You're gonna go to La
That sounds
Zapata.
pretty good.
You're gonna go to La Zapata and get free tamales with queso con rabo.
I was waiting to see.
What
if
is
someone-
that?
It's just basically
Cheese,
like
just cheese sauce?
just no, it's like
Yeah.
cheese and they put some like slice of I don't know jalapeno slices. But
All right, class, we
slice-
still have 10 minutes, so I want to squeeze every last drop out of you there. But there was a couple of questions, so I might address them to the class. In particular, somebody was asking about labs. I'm assuming lab is in person tomorrow. And we'll just have a normal lab. And in particular, I don't know, did anybody actually use that Google Sheet sign up to put in your lab groups? A couple. Okay, yeah. Something that I forgot to ask you in there was which ones of you, I wrote up 5 coding projects. So in theory, those of you that wanted to code could do that. Of course, I mentioned the projects to a friend of mine who happens to be a professional physicist that codes, and he's like, So I will say it this way, if you're willing to work, you can learn a lot from them. And but you probably should understand a little bit about force because it's very difficult to do, right? So I know that most of you have had high school physics, and just if you understand basically F equals ma, then we could usually work with you, right? And if you want to, if you're serious about coding, you should also I'll send out a video. You should actually do it. I know last week some of you didn't. I'm serious, right? If you want to make the best use of my time, you got to come in with at least doing the videos that I send you in advance. It's a 20-minute video. You code along. You can learn how to make animations. So if you're serious about that and you come in and then you haven't done that, I'll be like, well, just do a regular project because I don't want to deal with you. Right. So if you're serious about coding, I'll send you a video probably right after class. And then I'll look at that spreadsheet. If you're able to go into that spreadsheet and say, I want to code, please do that. That way I at least know, and I can kind of, and that way tomorrow when we come into class, I'll say, here's the options we got. And then you have one last chance to say, you know what, I'll just do a regular one. So we're going to be basically making videos of motion, making plots of motion like you're doing right here in class today, and then the idea is 3 weeks from now, you're going to give a talk, right? So you're going to stand up and have to explain one set of XT, VT, and AT graphs, right? And you're going to talk about, oh, here it was speeding up, here it was slowing down. Here's the video, watch the motion, see how it's speeding up. Oh, notice the slope is this, notice the area is this. All right. So that's lab. Okay with that? So if you can go in there, do that right away. If you want to do that right now, that's fine too. We got 7 minutes left in class. If you want to go in there, just so you don't forget. Those of you on Zoom, I hope you have it checked out and you're actually still hearing me, but appreciate the patience today. Hopefully the workbook was working. It looks like Jules has been helping you a lot, so I appreciate that. Thumbs up to her. Yeah, and so there's no point in really doing another problem, is there? I shouldn't start a whole new topic in 7 minutes. I wish I could, but I'm not going to. So let's just finish by doing some graphical problems. If you've already done some graphical problems and you think you're the bomb, you could try 2.30, or you could do any of the ones that say 2.29 and a fraction. So basically 35 and 36, pages 35 and 36 have some conceptual questions where you have to compare different plots. So you might think you're good at it, but if you actually compare them, it forces you to talk and think and work with your neighbors. So if you want a quick one, you could try one of those. And 2.30 and 2.31, pages 37 and 38 are a little bit different in the sense of you have to draw the graphs instead of interpreting the graphs. So yeah, try one of those if you've got a couple of minutes and just see if you can make 5 minutes of headway or pick a different problem out of the homework list. Just try and get a little bit more homework done and I'll be here to help answer your questions. Jules will probably take another pass after she helps the Zoomers one more time. All right, or like I said, go in there and tell me that you want to do coding, right? I know at least 2 of them are easy projects relatively. And I think 2 other ones are medium, and then one is fairly tough. Oh, we'll do that. Yeah, so we're gonna pick up page. We'll do these problems next time.
I'm trying to learn.
So yeah, if you're wondering what happens when acceleration is not constant, we're gonna address that in the next lecture, how to do calculus and separation of variables. Yeah, it's pretty fun. It's pretty fun. So that's what the 3rd lecture is
It's just
for.
algebra.
If you want to get out of here, I'm not offended as well. If you want to squeeze out of 5 more minutes, try and do it. All right. Good.
I never preach. So tomorrow. And we're gonna do this like coding project. No, I like it. I just, I'm not good at it. And I'm not good at it. That's it. I'm not good at it. I don't get it. No, I get it. Like I can't just like, I can't just sit there and write a code.
So now you know one of the things.
But
I think I'm better at that one.
do you? That's good. That's why we're ignoring I know.
Right, so at least then you're not guessing it all. You're guessing. Right, so last one is so let me get that there.
Gotta beat the car or, I'll be competing.
Usually the same thing.
Right there.
All right, good job. All good? Okay, okay. What do you think? You get somewhere today? Getting better at the graphs? All right, that's what we want. That's what we want. What do you think? Did you make some headway?
Sure.
Okay, I'll just finish up.
Dot Larson.
Oh, yeah, you're really close. Just finish that damn problem. Yeah, exactly. What do you think? I got it. Yep. All right.
Isn't it easy to just adding each other?
Yeah. Want to sound like.
Yeah.
This is.
Jacob Larson.
What's that? Oh, right.
So, like,
Hopefully, as the semester goes on.
Yeah, that's a long day.
Well,
I get away with it my whole day. Yeah. That's part of my. I didn't.
just takes.
I could have created.
It looks like that.
remember what's, it's, how many of them you were? Yeah.
Yeah, so just.
I've been putting off my.
Right? Oh, so, okay, yeah, yeah, does that make sense? Yeah. No, but- That was, no, yeah. So, yeah. This problem, I wanted to make sure you got it.
Situation that I picked up. It is a result of almost history. Take a look. Yeah. I see things. And I'm speaking. Yeah, exactly. So if you want, you can see these questions, they're more like, what is this? And it's very clear. So here, I just wanted to make sure I shouldn't all. Oh, okay, so generally speaking, yeah, so you can go. I'll say delta shock. That's always get possible. So the delta is always finalized, what she. So that's what you kind of want to do. So now that you know that, then yeah, okay. But it is weird, that's something that. They're good? Yeah. Yeah, maybe I said that something. You got a chance to watch those other movies. Yeah. Okay. I mean, a good goal would be chapter 2. So I mean, if we did like we get the next movie, that's going to set you up for the really, that's kind of the whole. Chapter 1, 2, and 3 are all done. Yeah, the years of time to leave it. Yeah, oh, right, that would take practice. Yeah. Yeah. Thank you. What do you think? Get it? Pretty easy. Make some headway or not? E final. E final is 12 meters per second. About someone else at its So then you could pick, do you agree you could pick this time or you could pick that time? Because it's going to slow all the way. So you can go to 0 or you can go to 1. Either way. Remember, this is 4 seconds. Time is not a way.
I have office hours too, so if you guys have more questions, I'm just chilling. We got the room if we want it, so. Maria, you all good? Robert? On Zoom? Just checking in with you here. I hope you're-
Yes, thank you.
What do you think, Maria? Are you able to learn something out of this or not on Zoom?
Oh yeah. I took 110 all on Zoom, so I'm kind of used to it.
Okay, all right.
Thank you. Have a good day.
You too. Okay, Robert,
Thanks,
how about
bye.
you? You good, Robert? Okay. If you're trying to talk to me, it's still on mute.